Hi everyone, this is a quick video just for one of the problems on the chapter 10 homework, problem number 3. And in this problem, if you read it, it says you got a 0.25 molar solution of the sodium salt of histidine, calculate the pH and the concentrations of all the histidine species. And so here's how we do it. First thing to do is look up the structure in the back of your textbook to figure out what it looks like fully protonated. And when you see that histidine fully protonated, which is not what we have in this problem exactly, but we have to do this first, is H3A2 plus. So with that in mind, we quickly draw the pKa diagram, and that'll help us figure out exactly what this is, the sodium salt of histidine. So pKa diagram looks like this. pKa at 1.6, pKa at 5.97, and 9.28. Fully protonated form goes in the bottom. And then we've got all of our other forms. Now, if we think about the sodium salt, all right, that is going to end up being the fully deprotonated form of histidine. Let me just quickly erase some of these little dots that developed here. So, oops. So we got our fully deprotonated form, and what we need to think about is which one of these 4 species it is, and so I think we're looking at this one right here. So what we're going to do when we think about how to do this problem, we're going to treat it like a monoprotic weak base, and to do that we're going to need all 3 Kb values. And we remember that we get the Kb values from Ka values like this. So Kb1 is going to be Kw over Ka3. And you can look up those values, but I got 1.92 times 10 to the minus 5th. And that particular Kb is going to have to do with this, this reaction. So we've got the deprotonated thing gaining its first proton from water. Like this. And then we've got our Kb2, which we calculate from Ka2 at 9.34 times 10 to the minus 9th. The reaction is this one. And finally, we need Kb3, which we find from Ka1. There's our Kb3 value, and it has to do with this reaction. All right, so I'm going to think about each of these 3 reactions as we then figure out what's going on. So everything really depends on reaction 1. And if we're going to treat the A minus as if it were monoprotic, then the first assumption is that Kb1 is going to be x squared over the formal concentration minus x for the A minus. And so I'm going to have to erase the most of this, but to give ourselves a little bit of space, or actually what I can do is really just go to the next page here. So when we think about that information, we'll go think about that first reaction we just wrote. And we know that 1.92 times 10 to the minus 5th is going to be x squared over the formal concentration minus X, where X is going to be concentration of that first amphoteric intermediate, but it's also going to be the concentration of OH minus. And when you do that calculation with your solve function, there's the value that we get. So we've solved for the first piece of information, and that is the concentration of this guy. And from that, then, we can also know what the concentration of hydroxide is. And then the hydroxide concentration gives us H+, which gives us the pH. So when we put the Kw over the hydroxide value to get H+, I get the H+ value of 4.6 times 10 to the minus 12th molar, and then my pH ends up being 11.34. That's the second goal of the problem, is to figure out the pH. All right, going back just for a second to that previous page. If we want to calculate the concentration of H2A+, we can see that we have to use the second Kb value, 9.34 times 10 to the minus 9th. And when we set up that equilibrium expression with the products over the reactant, this is what we get. Okay, and when we look back at that previous page, actually, we don't have to look at the previous page at all. It's right here in front of us. We see that the hydroxide concentration and HA are equivalent, equal, whatever. And so therefore, H2A+ equals Kb2. And that value is 9.3 times 10 to the minus 9th molar. All right, then, so we know now that the concentration of H2A+ is literally equal to Kb2. Then we can go back to that final equilibrium expression, and we see that that same species will continue to hydrolyze to make H3O2+ and some more hydroxide through Kb3. And so let's set up that equilibrium expression. Okay, so then we now move things around here before we do any plugging in of numbers, so we can isolate the concentration of H3A+. So we just remember that the value for OH minus is X. We remember that the value for H2A+ from the previous calculation here is Kb2. And so when we just rearrange that setup, we get the concentration of H3A2+. It's just going to be Kb2 times Kb3 over X. And we know the numerical values, so we plug those in. We get 1.4 times 10 to the minus 18th molar. All right, so then summarizing, the concentration of the first species, the actual deprotonated stuff, that's going to be the A- concentration. That's going to be our formal concentration minus X. And so our formal concentration in this little problem, what was it again here? 0.25 minus 0.0022. That calculation I forgot to do, 0.25 minus 0.0022. So we get 0.2478, and since 0.2478 is so close to 0.25, rounded to 2 sig figs, there's our answer. Okay, so we've got the concentration of the deprotonated form, and we've got the concentration of the monoprotic intermediate, got a concentration of the diprotic intermediate, and then the fully protonated form.